In our previous videos, we've seen a simulation study to compare two sample proportions. We also identified the conditions required to get a z distribution for comparing two proportions, as well as what the mean and standard deviation for that sampling distribution would be when certain conditions are satisfied. In the example that we had looked at previously, looking at coronary artery disease and earlobe crease, we saw that those conditions were not satisfied, so I'm introducing a new example, cash for quitters. In this example, an effort was made to reduce healthcare costs at General Motors. In that study, General Motors sponsored a study to help employees stop smoking. In that study, half of the subjects were randomly assigned to receive up to $750 for quitting smoking for a year, while the other half were simply encouraged to use traditional methods to quit. None of the 878 volunteers knew there was a financial incentive when they signed up. At the end of 1 year, 15% of those in the financial rewards group had quit smoking, while only 5% of those in the traditional group had quit. The question is, do the results of this study provide convincing evidence that a financial incentive helps people quit smoking? First, I'd like you to stop and think whether this is an experiment or whether this is an observational study. Then, I would like you to stop and think and identify what is the explanatory variable in the study and what is the response variable. So, is this an observational or experimental study? What is the explanatory variable? And what is the response? Pause this video, answer those questions, and then check your work with mine when you pick it back up. This is an experimental study. It's an experimental study because we are doing random assignment of participants to one of the two groups. Some participants are being assigned to a financial incentive to quit smoking, and others are randomly assigned to just be encouraged to use a traditional method. So, because we have that manipulation of what level of the explanatory variable people are getting, there is an experimental study going on. That way, we are eliminating confounding variables in terms of what is helping motivate people to quit smoking. Our explanatory variable, as I've just possibly alluded to, is therefore the group. Well, of course it is the group. So the levels are traditional method or the financial incentive. So they were either grouped into whether they received the traditional method or the financial incentive. Notice that financial incentive is not a variable and traditional method is not a variable. It's the incentive or the encouragement that they receive for actually quitting smoking. The response variable is whether they quit smoking. In this case, the levels are yes or no. So if they did quit smoking, they get a yes, and if the participant did not quit smoking, then they get a no. So the variable is quit smoking, and the participant either did or did not. Both of our variables, the explanatory and the response, are categorical. And remember, I've identified that this can be a tricky thing, so getting your variables straight and identifying them and their levels is really important, especially when dealing with categorical variables. The next thing we want to do, now that we've identified our question and the variables of interest and that this is an explanatory study, is to state our hypotheses. We want to translate this question into a set of statistical hypotheses. What we might want to say is, if there were no relationship between the group or the incentive that they received and whether someone quit smoking, what would that mean in terms of the probability that someone quit smoking? If there were no relationship, then the true difference in the true proportions for both the financial incentive and the traditional method groups would be the same. That is, the difference in proportions would be 0. We could also write this as the proportions are equal. Pi 1 equals pi 2. If there is a relationship, that is, if the financial incentive is useful, because we're saying, does the financial incentive help people quit smoking, then that means that not only are the two proportions not the same, but one of those proportions is higher, that having a financial incentive increases the probability that someone quits smoking versus just traditional methods. So pi 1 is greater than pi 2, which is the same as saying pi 1 minus pi 2 is greater than 0. But so that we can be clear in what this direction of inequality means, we have to be sure to define our parameters. So pi 1 and pi 2 are the true chances or probabilities of quitting smoking under a financial incentive and traditional methods. Respectively. So pi 1 is a probability that someone successfully quits smoking using the financial incentive, and pi 2 is the probability that someone is a successful quitter when they use just the traditional method. And in this way we can see that the alternative hypothesis is saying that the probability of quitting using the financial incentive is higher than the probability of quitting using just a regular traditional method. Oh, good. What are the conditions required for this test to be valid? So our conditions or assumptions, well, first we need independent samples. Has this been satisfied? It has been satisfied. They randomly assigned participants to one of those two groups. Participants were randomly assigned to either receive the financial incentive or to just be encouraged using the traditional methods. Yes, we did random assignment to only one group. We also need random samples. And for the same reason, this has been achieved, because we did random assignment. Participants were randomly assigned, and in this way we have eliminated any confounding variables. So our independent and random samples have been achieved through random assignment. People were assigned to only one of the two treatments, and they were assigned randomly. We also need a categorical response and a categorical explanatory variable. This has been achieved because both smoking status or quitting status after 1 year and incentive, that is financial or traditional method, are categorical. So we're good there. The last condition that we have to satisfy, I apologize for all these pop-ups, but I'm not going to edit them out because I don't have time for that, is that we have a large enough sample so that there are at least 10 successes and at least 10 failures in each group. That is, we need at least 10 people to have quit smoking under the financial and traditional methods, and we need at least 10 people to have not quit smoking under the financial incentive and the traditional method. So we need at least 10 successes and 10 failures in financial and traditional methods groups. Has that been satisfied? Well, we don't have the raw numbers, but we do have probabilities. If we look back up here, we see at the end of the year, 15% of those in the financial rewards group had quit smoking, and only 5% of those in the traditional group had quit. We also know that it was a 50-50 split between those who had been assigned to each of the method. So even though there are 878 total volunteers, we know that half of those 878, or 439, were in the financial rewards group, and 439 therefore were in the traditional methods group. So N1 equals 439, and N2 equals 439. And from here we can check, does N1 times P1 hat is that greater than or equal to 10? And we can do N2 times P2 hat, is that greater than or equal to 10? And we can also do N1 times 1 minus P1 hat, see if that's greater than or equal to 10, and N2 1 minus P2 hat, and see if that is greater than or equal to 10. N1 P1 hat is going to be 439 times 0.15, because 15% of the financial rewards group quit. It turns out that 15% of 439 is 66. That's greater than 10, so we're good. We want to do the same thing for those who did not quit, so that's going to be 439 times 1 minus 0.15. So that's 85% of the 439, that's 373. That's good. For the non-financial rewards group, so for the traditional methods group, that's 439 times 5%. So 22 people quit in the traditional methods group, and everyone else in the non-traditional methods group, or 95% of them, did not quit, which is 417, which is way more than 10. So we have success. So we have a large enough sample in order to use the normal distribution. So we do have large enough samples for the z-test to be valid. Yay! We've identified our hypotheses, we've defined our parameters and context, and we've also gone through and checked our conditions in order to make sure that this theoretical test is going to be valid. The next thing we need to do is identify our test statistic and p-value. Because this is a z-test, our z-test statistic, z-obs, is going to be the same form as every other z-test statistic that we have seen. It's going to be our statistic minus the parameter of interest divided by the standard error of our statistic. Our statistic is P1 hat minus P2 hat. Our parameter comes from the null hypothesis, so that's going to be the hypothesized difference between pi1 and pi2. From a previous video, we learned how to estimate the standard error of the statistic, and that's going to be the square root of p hat 1 minus p hat times 1 over n1 plus 1 over n2. Remember, p hat is this pooled value. If for real pi1 and pi2 are the same thing, as we believe under the null hypothesis, then we're going to take all of the successes in group 1, all of the successes in group 2, and add them together and come up with one overall estimate for the true proportion of people who quit smoking regardless of their method. So p hat is that estimate. So p hat is the total number of quitters divided by the total sample size. In this case, we observed that there were 66 people who quit with a financial reward, there were 22 people who quit under the traditional method, and there were 878 people total in the sample, giving me a p hat of 1. So on average, I would estimate 10% of people to quit regardless of the method, if there were no difference between the two populations. So now I can find my test statistic. P1 hat minus P2 hat is the difference in my sample proportions, so that is 0.15 minus 0.05. 15% of the people in the financial rewards quit, 5% of the people without a financial reward quit. The hypothesized difference is 0. So this comes from HO as always. For the standard error, I just plug in. So I use 0.1 times 1 minus 0.1, where that 0.1 is the value that we just found here. And then I multiply times 1 over n1, which was 439, plus 1 over n2, which was also 439 because I had equal-sized groups. Altogether, my test statistic, or my z-obs, is 4.94. Now my question to you, and I would like you to think about this, is this a big test statistic or a small one? That is, do I have a big z-score or a small z-score? And also, how would I interpret this? Please pause this video for just a moment and think about how you would answer that question. This is a big test statistic. A z of 4.94 means that we have observed a sample difference that is 4.94 standard errors larger than the hypothesized value of 0. This is big. Remember, we usually look at the rule of greater than 3 or less than -3 when we're trying to identify whether we have a big standardized value, that is, whether our z or t-scores are big. And 4.94 is definitely bigger than 3. However, we also want to look at the actual effect, this difference of 0.15 and 0.05. Under the financial incentive, 15% of people quit. Without the financial incentive, 5% of people quit. So that's a difference of 10 percentage points. Is that a big effect? Yeah, kind of, right? We've seen an increase of about 10 percentage points by just using a financial incentive. And if we think about all the ramifications of smoking and getting people to quit smoking, especially earlier on, then getting even a 10 percentage point change in the number of people who quit by using a financial incentive, that could pay dividends in the long run. So what might we conclude? Our p-value in this case is going to be less than 0.0001. If we think about a normal distribution, we have something that's really far out there. We've observed a z-score that's bigger than 3, and so our test statistic is really unusual and our p-value is tiny. It's in that tiny little right tail. So what would you conclude? What decision would you make? I might say something like this. We have strong evidence that using a financial incentive instead of traditional methods to encourage people to quit smoking causes people to quit at a much higher rate. Because we have a large effect and a small p-value. So we have a very small p-value. If there really is no difference in the quitting rate between those who do and do not receive a financial incentive, we're going to observe something like this less than 1/100th% of the time. Right? So that's pretty strong evidence. But then we also want to look at that effect size. And we observed an increase of 10 percentage points for people who receive a financial incentive. People who receive a financial incentive there is a 10 percentage point increase in the probability, or there's a 10 percentage point higher probability of people quitting smoking when they have a financial incentive versus those who don't. And that's a really sizable effect. So altogether, because there's both a large effect and a small p-value, this is giving us really compelling evidence of a meaningful relationship between the financial incentive and having the probability, the likelihood of people quitting smoking. And I wanted to emphasize that we can talk about this causal relationship, that having this financial reward causes people to quit smoking at a higher rate or with a higher probability, because we did an experiment. We identified this as an experimental study because there was random assignment of treatments to subjects, and that eliminates confounding. So all those other things that might get people to quit smoking, like maybe family obligations or other concerns for their health, we randomize those out. The only difference between these two groups, or the only substantial or meaningful statistical difference between these two groups, is the financial incentive. All those other possible variables that could explain these differences have been randomly assigned and eliminated. So the only possible explanations are chance and cause, and because this p-value is so small, we can attribute these differences to cause. The next video, we are going to look at these same data, and we're going to look at a confidence interval for the true difference in proportions.